Hi, we are Group 2, and this is our IC Engines Lab presentation. Generative Energy Systems Incorporated has developed a unique generator based on an internal combustion engine that can be powered by either compressed air or propane. A 48-volt BLDC regenerative motor is attached to the engine to start the engine and generate electricity to be stored in battery packs. This experiment is focused on finding the optimal control parameters for power generation. This is achieved by characterizing both the mechanical properties and fluid exchange properties of the engine. To determine the optimal control parameters for the IC engine, the mechanical properties of the engine must be determined. The full four-stroke cycle of the engine must be characterized, and the engine output with simulated combustion must be modeled. The mechanical properties of the IC engine include frictional torque and flywheel inertia. To determine these, the engine begins with the engine head off with no air injection. The motor torque and angular position is obtained for low, medium, and high speeds by turning the potentiometer between 0 and 1 full rotation in forward operation. This data is plotted as motor torque versus angular position. The frictional torque is found by observing the average steady-state torque, and the flywheel inertia is determined by calculating the acceleration from 0. This process is then repeated for one velocity with only one flywheel. This frictional torque is then used to calculate frictional work. To characterize the full four-stroke cycle of the engine starts with the engine head on, but there is still no air injection. The engine head will allow us to determine the work due to air compression and expansion, as it will cause the air to compress or expand in different strokes of the cycle. Because no air is injected, we can assume that there is no heat transfer during the power stroke because the expansion is adiabatic. With the engine head on, the motor torque and angular position is obtained for low, medium, and high speeds by turning the potentiometer between 0 and 1 full rotation in forward operation. This data is then used to determine the work due to air and therefore characterize the full four-stroke cycle. Lastly, the engine output with simulated combustion must be modeled. To do this, the engine starts with the engine head on and air injection enabled. Now that the air injection is enabled, our assumption for the expansion during the power stroke changes from being adiabatic to being isobaric, i.e. there is constant pressure. This allows us to more accurately characterize the work output of the system.
The first step in each week's lab is to calibrate the torque sensor. To do so, weights and the moment arm length are measured. The weights are then stacked one by one to the end of the moment arm and then removed in the same way. Voltages are recorded for each addition and subtraction of weight. The plot here is the calibration data from week 2, and you can clearly see the effect of hysteresis on the system by looking at the horizontal offset of the raw data points. Once the data is collected, the points are input to a York regression that provides the gain, offset, and corresponding uncertainties. The gain and offset create the calibration equation that we use to determine torque from voltage. To average torque values into 10-degree bends, a for loop is used. The first step in each loop determines the indices correlating to the start and end of the current bend. The next step is to grab the torque values corresponding to the indices found in the previous step. Lastly, these values are averaged. Thus, we have one average torque value for each bend. This whole process is important in determining work values using the Riemann sum method.
So to re-summarize what all we've been doing so far in terms of the work energy balance, which is listed at the top, for the first round of experiments, we removed the head from the engine. What this does is completely removes the work due to air term. We neglect discrepancy in piston work. And then by taking that data, we segmented it to the steady state range, which removed the left-hand side of the equation. We were able to calculate the work due to friction. And then knowing that and looking at the full transient, we are able to calculate the inertia of the flywheel. In the second week of experiments, everything we were doing was just to quantify the work due to air expansion and compression without injecting any air into the system. And then what we will be doing for the third round of experiments is we will be injecting air into the system to quantify the power stroke work. Using this value from the experimental and theoretical calculations, we'll come up with a work discrepancy value, and we can compare that to the uncertainty in the data to draw a conclusion on the system and sensors.
These graphs show the amount of torque being provided to the shaft by the electric motor. In all tests shown, the engine was cycled with a head attached. The upper subplot corresponds to the engine running without the flywheel, while the lower subplot to the engine running with all three flywheels. The first peak in both plots represents the compression stroke. This stroke was used to compare how the engine runs with and without flywheels. When the engine was run without flywheels, the maximum torque supplied by the motor to the engine's shaft was 7.94 Newton meters. On the other hand, when the engine was run with all three flywheels, the maximum torque achieved was only 3.42 Newton meters. That is 56.9% lower. Moreover, as a measure of torque variation, the maximum torque amplitude for the engine running without flywheels was 4.93 Newton meters. On the other hand, the maximum torque amplitude achieved with a flywheel was 0.96 Newton meters. That is 80% lower. Hence, running the engine with a flywheel makes it run smoother and with lower torque magnitude peaks. This is because when the engine is run with a flywheel, the flywheel can store energy and then supply this stored energy to compress air during the compression stroke. These average torque curves were used to find the work due to air.
After we calculated the average torque of one full engine cycle, we can identify each stroke of a cycle by each 180 degrees of a complete 720 degrees of a full cycle. The work of each stroke is then calculated using the sum of data points on the torque angular displacement graph times 10 degrees, which is the increment size. The results are shown in the table at the bottom. And the uncertainties are calculated using the inherited sensor uncertainties combined with the uncertainties of the York regression. And those are the uncertainty results.
So to discuss what we'll be doing in the third round of experiments, which have not been conducted yet, the two main things that we'll be doing is we'll be tuning the engine. This is when we're changing the injection angles of the pneumatic air to experimentally find the optimal range to increase the power stroke work, which is maximized by finding the largest torque during the power stroke cycle. The other thing that we'll be trying to do is modeling the discrepancy, which is a comparison between the theoretical and experimental work due to air. This will be compared to the uncertainty of the work due to air. And if the discrepancy is greater than the uncertainty, the model needs to be improved. However, if the discrepancy is less than the uncertainty, then we will need better sensors for further experiments. And so thank you for listening, and hopefully it was enlightening.